Good morning, professors and honorable guests. I'm Gabriel Loy, and he is York. We are from GT College, and we would like to present our project on the investigations of fundamental solutions to the Pell's equations. This presentations consists of 4 parts, which is the backgrounds and the aim of studies, the case of fundamental solutions to Pell's equations, and we would also like to answering a question that why there are large values of fundamental solutions exist. And finally, we would also like to give some comments on our projects. So first, we would like to give some backgrounds. And the Pell's equations is defined as x squared minus dy squared equals to 1, which is a quadratic Diophantine equations. It can be solved in positive integer x and y for any non-square positive integers d. A traditional method of periodic continuous fractions is used to solve Pell equation for its fundamental solutions. Infinitely many higher order solutions can be generated based on the fundamental solutions. We can express square root d as a, b1, b2 until bm, which is a periodic continuous fraction, and m is the period. And the fundamental solutions is related by P over Q, which is a b1, b2 until bm minus 1, which is a periodic continuous fraction also. And we will like to figure out some disadvantage of the method of using periodic continuous fractions. First is it is time demanding, as it's to find out such a continuous fraction and hence the fundamental solutions for a given value of d, except for using some technological help. And the second is we think that it is lack of connection between fundamental solutions of Pell's equation for different values of d. Our method is by finding the fundamental solutions to Pell equations for d equals to 2 until 100 to 50 by the web page Pell calculator, followed with verifications by substituting them into the Pell equations. By inspection, we find some regulation between solutions for a series value of d. We believe the fundamental solution can be grouped in case. Hence, the fundamental solutions can be formulated depending on the functional structure of d. This gives a powerful method to obtain the fundamental solution. We also found a large values of fundamental solution, which is the values in a green box as shown. As shown that the fundamental solutions in green box is much larger than that in a red box and the others. We will also like to try to answering why there are such a large fundamental solutions. Large value of fundamental solutions exist. As second, we would like to go into some cases of fundamental solutions to the Pell's equations. The first case, which is d equals n squared minus 1, as shown from the values in the blue box, it is easy to figure out the fundamental solutions to be x1 equals to n and y1 equals to 1. As shown when n equals to 2, which is the parameter d will be 3, and when n equals to 3, when the parameter will be equal to 8, and the corresponding fundamental solutions for x will be 2, 3, as shown. And we'll also figure out that there is a trend that all of the fundamental solutions value of y will be 1 also, and hence we will figure out and we can make such conclusions. And the second case for d equals n squared plus 1, we will also by doing the same thing and by inspecting the fundamental solutions. And from the values in the red box, the fundamental solutions are found to be x1 equal to 2n squared plus 1 and y1 equal to 2n. And the third case of d equals n squared minus 2, and as shown, when n equals to 2, 3, 4, and 5, the corresponding parameter d will be 2, 7, 14, and 23 respectively. And fortunately, we found out that the fundamental solutions for y1 would be 2, 3, 4, and 5. And hence, from the values in the green boxes, the fundamental solutions are found to be x1 equals to n squared minus 1 and y1 equals to n. And the fourth case, using the same method for d equals to n squared plus 2. From the values in the green boxes, the fundamental solutions are found to be x1 equals to n squared plus 1 and y1 equals to n. Unfortunately, there is an unsuccessful case for d equals n squared plus 3, We found that as d increases, as shown that when n equals to 2, 3, 4, and 5, the corresponding d's will be 7, 12, 19, and 28. However, we'll find out that the fundamental solutions for x1 and y1, which is either increase or decrease. The solutions is fluctuates, as shown in the red box, and the formulations of the fundamental solutions will not be trivial. We will only work out some special case when n equals to 3k, which is n is a multiples of 3, which is shown in the report. And for the fifth case, when d equals to n squared minus 4, we'll find out that for odd n and even n cases, the fundamental solutions of x1 and y1 will be different. As shown, when n equals to 2, when n equals to 3, 5, and 7, and 9, the fundamental solutions will be different. The fundamental solutions of y will be 4, 12, 24, and 40. And when n equals to 4, 6, and 8, the fundamental solutions will be 2, for y will be 2, 3, and 4. And as shown, a detailed fundamental solutions of algebraic structure will shown for odd n and even n. And in similar cases, when d equals to n squared plus 4, we found out that for odd n and even n cases, the fundamental solutions of x1 and y1 can be formulated, and as shown. So we would also like to answering a question that why there are large values of fundamental solutions we found. So we begin on investigating 3 different cases, which is d equals to 71, 79, and 313. We will begin in d equals to 71. When d equals to 71, as 71 is almost the middle part of the 2 consecutive square numbers, and we found out that the square root of d would be if it's written to a continuous fraction, the period is 8, and the fundamental solution is relatively larger when d equals to 79, as shown. It is because 79 is much nearer to one of the square numbers, and the period for square root d would be 4, and the fundamental solutions will be much smaller, as shown. And the third case, when d equals to 313, we'll find out that the square root of d is a much, much longer continuous fraction, can be written as, and hence the consequence of fundamental solutions will be large. It is due to the long period of square root of 313. And finally, we would like to give some comments on our projects. The first is from case 1 to case 6, the formula of the fundamental solutions are completely worked out so that they can compute it directly. And the second is the large values of fundamental solutions occur when d is prime and close to the middle to the consecutive square number. In this case, the square root of d can be expressed as a periodic continuous fraction with a long period. For example, when d equals to 313, and it is a prime, which we figured out in the previous slides. And this is the end of our presentations. Thank you.